Is it done?
No, sir.
Yes, sir.
1 minute. Sir, can you click on? No, not this one, sir.
I didn't get you.
Yes. Can you scroll it down, sir? That down part.
Here, what we can say is that the length of arrows. Okay, the length of arrows. So this is what is called gravitational field lines. Here, these are called gravitational field lines. Field lines. So note, gravitational field lines are imaginary. Lines are imaginary lines. Understood? They do not exist in reality. In fact, the concept of gravitational field itself is imaginary. Now here, one more thing is that the gravitational field strength or gravitational field intensity, gravitational field, you can say intensity or strength, is proportional to the length of the arrows used to represent a field at a point. At a point is proportional to the length of the arrows used to represent gravitational field at that point. Further logic. So, in fact, what we must be doing is that the proper representation would be, you see, as you're moving away, as r increases, what should happen to the value of e bar? Since e bar is equal to minus g capital M by r square in r cap direction, that is magnitude of E. Magnitude of E is what is happening, it is inversely proportional to r square. Is that right? It's inversely proportional to 1 by r square. So that means as you move away, what should happen to the length of the arrow? Length of the arrows must decrease. So in the given case, if you want to rectify this, what I'll do is that here, as you're moving away, the length of the arrows, what must happen? It must decrease. Understood the logic?
Yes, sir.
when we are close to the object, the field is strong. But as you move away, the field strength decreases. That can be better represented in this way. Yes, that's good.
So at infinity, the gravitational field strength will be zero, right?
At infinity, yes. Is it done copying?
Yes.
Now, in fact, here itself, let me tell you that there is one more way of representing drawing the field lines. Clear? There is one more way of drawing the field lines. Uh, so there is one more way of drawing field lines. There, what you do is that if you have a block of mass m, let's see if you have a block of mass capital M, then you represent the field lines in this manner. That means the field lines are continuous. Then in this case, how do you show that the field strength is huge? Let's say there you are having mass, and here, if at all you are having twice that of mass, you want to show that the field strength is definitely the field strength will be double, right, at a given point, because mass is twice, so the field strength will also be twice. Previously, what you would have drawn an arrow twice that of the length of that of m. If you want to draw it for 2m, then you would have doubled the length of the arrows. But here in the given case, you cannot. There is no information in the length. Clear? There is no information in the length. What information is there? Always the tangent drawn, okay, proportional to length of arrows, or we can say number of arrows, number of field lines used to represent the value of E bar. That means here if mass M is having 1, 2, 3, 4, 5, 6, 7, 8, 8 field lines, then 2M must have how many? 16 field lines.
Yes, sir.
Got the logic? You see, by just looking at this diagram, what is happening is that we are getting this psychological feeling that this 2m is definitely a larger mass here. So either you represent it using the uh, length of the field lines or length of the arrows used to represent field lines, or the number of field lines. Got the logic?
Yes, sir.
Now, in fact, you can talk about one more thing about field lines, that If at all assume that there is an electric field, clear? If at all there is an electric field, and if you release a particle of mass m, the particle of mass m will always travel in this direction of the field lines. Understood? It will travel always along the gravitational field line. Clear? Any mass subtended, released, any mass subtended in a gravitational field shall follow the path of field lines. Field line. Understood? That means along a curve at any instant, we can say the tangent drawn to field lines will represent the gravitational field intensity at that instant. Understood the logic? At any instant, the tangent drawn to that particular point will represent the field strength. So the particle, what will happen is that it will travel along the field lines. Now, in fact, based on this concept itself, what we can see is that, you see, particle is supposed to travel along the field lines. What will happen? Let's say there are two field lines intersected over here. And what I've done is that I've released a block of mass, some small mass m. It will reach at this point. From there, where it has to move, where it will move. Let's say.
So will it move in the field line of bigger length?
No, that's not correct. Because if there are two field lines, that means there are two possibilities. Then the object, it cannot decide where it has to move. So the thing is that we say that gravitational field lines do not intersect. Not only gravitational field lines, most of the fields, they do not intersect. Got the point?
So, but how is it possible now if, let's say, a mass, bigger mass and smaller mass are placed side by side, then both will have gravitational field lines, no? Then they will intersect, right?
That is, the gravitational field at a given point is the resultant of two or more gravitational fields. The gravitational field, did you get the logic? If you say that there are two masses, two fields are supposed to be there, then what will happen is that the two fields will produce a resultant field, gravitational field at a point is the resultant of two or more fields. That is, net electric field is equal to E1 bar plus E2 bar plus so on up to En bar. So the field lines will, the particle will travel along the net electric field.
Okay.
The particle shall travel along the net or resultant gravitational field. Got the point? So these field lines, they do not intersect. This is wrong. They come very much close and they just separate, but they do not intersect. They come close and leave, but they do not intersect. This is correct.
So according to this point, if two masses are placed close by, then their gravitational field lines add up, and that will become the net gravitational field.
Yes,
The
yes.
okay.
So then, what will be the like net magnitude and direction of that combined gravitational field?
It's a vector sum. You know how to add vectors, right?
Yes, sir.
That's it.
Okay.
Is it done?
Yes.
Uh, so we'll stop today's class here. In tomorrow's class, what we'll do is that, okay, this is the concept of gravitational field. Okay, and in tomorrow's class, what we'll be doing is that we'll be talking about the concept of gravitational potential. But one thing, if you can remember, if you can notice, what we used to write for the acceleration due to gravity, if you remember, acceleration due to gravity for Earth, we said
Equal
that,
to G M by R square, right?
yes. So we said that if this is capital M, this is Earth, this is block of mass small m. We said that it will be experiencing a gravitational force, that is Fg. This is Fg. The magnitude wise we are writing it. So this is of R. The separation between them is R. Then we said that Fg is equal to G capital M small m by R square. Clear? If you wanted to write it in vector form, this would have been Fg bar and this would have been minus Fg bar. So for minus Fg bar, this is minus Fg bar. If you put it in this manner, so what we get Fg bar will be equal to G capital M small m by R square in minus R capital
Minus
M.
R.
So this was the force. Now when you divided this force by mass, then we said that this was nothing but acceleration due to gravity. Remember, we called this term
Yes, sir.
as
Yes,
acceleration due to gravity.
yes, sir.
But if you can see, this is nothing but the concept of field, right?
Yes, sir. Force acting per
That is
unit mass.
intensity.
So that means what we are saying is that for Earth, E bar and G bar, they represent the same thing. Is that okay?
Yes, sir.
That means this gravitational field can be for any object in the space or for multiple objects, anything. That means the force, the influence is what is called gravitational field, but the influence, sorry, the gravitational influence of Earth is called acceleration due to gravity. Got the logic?
Yes.
So from tomorrow's class, what we'll be doing is that we'll not call it as E bar, but we'll be calling it as G bar. We call it as acceleration due to gravity. When I call about acceleration due to gravity, that is nothing but the gravitational field intensity of Earth. Got the logic?
Yes,
Yes,
sir.
sir.
Understood? So copy this. We'll meet tomorrow. Thank you.
Sir, can you send the
What?
no? Can you send the rotation notes, sir? Because I think last page you said you'll send and you did not send. We have to write it
Okay.
last page.
I'll send it now.
Yeah.
So can I send this one also, sir?
This one. You have copied it, right?
Yes, sir.
Fine.
I joined little late, sir.
So, okay, sure. I'll send.
Thank you, sir.
Okay, thank you. Bye.